Improper integrals. Improper integrals are integrals where either the first case, what we call type 1, if the interval is infinite. So notice that we have this integral here, and if we were to write that symbolically, we would have the integral from, say, a to infinity of that f of x with respect to x. So this is an infinite integral. All right, and so that's our first type of an improper integral. And our second type is where the interval contains an infinite discontinuity. So if we were to consider, if again I were to call this function f of x, if I were to consider, say, the integral from a to c of f of x dx, that would be an improper integral because there's an infinite discontinuity at c. Also, if I were to consider the integral from a to b of f of x dx, that would again be an improper integral because of the infinite discontinuity. So in this section, we're going to see how we can deal with these improper integrals. If we have a type 1 integral, improper integral, what we do is we change the infinite interval to a finite interval and then take a limit approaching infinity. So the basic idea is if we have, if we sort of focus right here, if we have the integral from a to infinity of f of x dx, what we do is we rewrite it as a limit with t approaching infinity of the integral from a to t of f of x dx. We evaluate this integral from a to t, and then we apply the limit with t approaching infinity. And similarly, if we have a negative infinity, we replace that negative infinity with a t and take a limit as t approaches. That should read negative infinity there. And if we have an integral from negative infinity to infinity, we can break that up and evaluate those integrals. Now, we have to see if these limits exist. If the limit exists, we say that the integral is convergent. And if that limit does not exist, the integral does not converge. So let's see an example. We are asked to evaluate the integral from 1 to infinity of 1 over x dx. So this is an improper integral, since we have the upper limit is at positive infinity. And so what we will do is we will instead evaluate the limit as t approaches infinity of the integral from 1 to t of 1 over x dx. All right, now this is a fairly simple antiderivative. So we would now have the limit as t approaches infinity of natural log absolute x from 1 to t, which is the limit as t approaches infinity of the natural log of, well, since the natural log of absolute t, well, t is going to be positive infinity, so it's going to be just natural log t minus the natural log of 1. Now, the natural log of 1 goes to 0, right? The natural log of 1 is equal to 0. So we're just focusing now on the limit as t approaches infinity of the natural log of t. Well, as t approaches infinity, the natural log of an infinitely large number is still infinitely large, and so this approaches infinity. And so what we would say is the integral from 1 to infinity of 1 over x dx does not converge. let's keep that in mind. We're going to actually reference this exercise later on in this section. All right, here's another example. Here we're asked to evaluate the integral from 1 to infinity of 1 over 2x plus 1 cubed dx. So what I will do is rewrite this as the limit with t approaching infinity of the integral of 1 from 1 to t of 1 over 2x plus 1 cubed dx. Now to evaluate this integral, I'm going to use a substitution. I will let u equal 2x plus 1, and then du would be 2 dx. And notice that if u equals 1, that implies that u equals 3. And if u equals t, I'm sorry, I should say if x equals 1. Right? If x is 1, that implies that u is 3. And if x is t, that implies then that u would be 2t plus 1. So then this becomes, now if du is 2 dx, that means I would need to multiply this dx by 2, and that means I would need a 1/2 on the outside of the integral. Now since that 1/2 is a constant, remembering our rules for limits, I can bring that 1/2 left of the limit. So I'd have 1/2 limit t approaching infinity of the integral. Now since I'm making the substitutions, I'm going to change the limits of integration from x equals 1 to u equals 3, and from x equals t to u equals 2t plus 1. And I have u to the negative third du. So then this becomes 1/2 limit t approaching infinity. The antiderivative of u to the negative third would be negative 1/2 u to the negative second. And we will evaluate that from 3 to 2t plus 1. And again, since we have this constant, this negative 1/2 is a constant multiple, we are allowed to bring that outside the evaluation and then outside the limit. So then we have negative 1/4 limit t approaching infinity, and now making the appropriate substitutions, I would have 2t plus 1 to the negative second power minus 3 to the negative second power. All right, so now let's focus. Now 3 to the negative second power, that's just 1/9. But that 2t plus 1 to the negative second, let's focus on that. As t approaches infinity, 2t plus 1 would also approach infinity. And then 2t plus 1 to the negative second power, well, that would be 1 over 2t plus 1 to the positive second. And so then that would approach 1 over infinity to the second power. Well, infinity to the second power is still infinity. So that's 1 over infinity, which approaches 0. So what we have now is that this, after taking this limit, right, so this is a little bit of side work. So now we have then negative 1/4, and as t approaches infinity, we would have then 0 minus 1/9, and 0 minus 1/9 is negative 1/9 times negative 1/4 is 1/36. So the integral converges to 1/36. And so we would write then that the integral from 1 to infinity of 1 over 2x plus 1 cubed dx is equal to 1/36. And we say that this integral converges. Evaluate the integral from 0 to infinity of 1 over the 4th root of 1 plus x dx. This would be a good one to try on your own. So now would be a good time to pause. Alright, so like with the previous exercises, I will rewrite this improper integral as the limit with t approaching infinity of the integral from 0 to t of 1 over the 4th root of 1 plus x dx. I will make the substitution u equals 1 plus x, which implies that du is dx. Alright, and if x equals 0, this implies then that u equals 1, and if x equals t, this implies then that u equals 1 plus t. So, I don't need to multiply by anything since du is equal to dx. So my integral then becomes the limit with t approaching infinity of, now I'm switching variables here from x to u. So I would be from 1 to 1 plus t of u to the negative 1/4 du. So then this is the limit as t approaches infinity of 4/3 u to the 3/4. From 1 to 1 plus t. Again, I can bring this 4/3 outside the evaluation and outside the limit. So then this becomes 4/3 times the limit as t approaches infinity of 1 plus t to the 3/4 minus 1 to the 3/4. Now 1 to the 3/4 is 1. That's not a problem. But what happens to that 1 plus t to the 3/4? So let's focus on that. As t approaches infinity, 1 plus t would also approach infinity. And then 1 plus t to the 3/4 would approach infinity to the 3/4. Now, infinity to the 3/4, if I take infinity to a positive exponent, that's going to give me an infinite number. And so then this 4/3, this limit would then approach 4/3 of infinity minus 1. And so this does not converge. Alright, consider the integral from negative infinity to 0 of 2 to the r dr. This would be another opportunity for you to try this one on your own, so now would be a good time to pause. Alright, since I have the lower boundary at negative infinity, I will rewrite this as the limit, t approaching negative infinity, of the integral from t to 0 of 2 to the r dr. Now, I remember from the previous chapter that the integral of a to the r dr is a to the r over the natural log of a plus a constant. So, I would now have the limit as t approaches negative infinity of 2 to the r over the natural log of 2 from t to 0. Now that 1 over natural log of 2 is a constant, and so I can bring that outside the evaluation and again outside the limit. And so this becomes 1 over the natural log of 2 times the limit with t approaching negative infinity of 2 to the 0 minus 2 to the t. Two to the 0 is 1. What happens to 2 to the t? Alright, so let's see. As t approaches negative infinity, 2 to the t would approach 2 to the negative infinity, which is 1 over 2 to the infinity. 2 to the infinity is large, so it becomes 1 over infinity, which approaches 0. So we'd have 1 over the natural log of 2 times, remember 2 to the 0 is 1, minus, and 2 to the t would approach 0 as t approaches negative infinity. So this then equals 1 over the natural log of 2. And so we would say then that the integral from negative infinity to 0 of 2 to the r dr is 1 over the natural log of 2. And that the integral does converge. For what values of p is the integral from 1 to infinity of 1 over x to the p dx convergent? We've already shown that for p equal to 1, which therefore gives us the integral from 1 to infinity of 1 over x dx, this does not converge. In fact, that was the first example in this section. All right, so now, what if p is not 1? Well, let's see what happens. All right, so if p is not 1, then the integral from 1 to infinity of 1 over x to the p dx can be rewritten as the limit as as t approaches infinity of the integral from 1 to t of x to the negative p dx. All right, so we have x to a power, and so since we've now said that p is not 1, then we can evaluate this integral. We can find this antiderivative, and so that would then be the limit t approaching infinity, and I would have x to the negative p plus 1 over negative p plus 1, evaluated from 1 to t. Now 1 over negative p plus 1 is a constant. We can bring that outside the evaluation and therefore outside the limit. So I'd have then 1 over, and I can write negative p plus 1, I'll just leave it as negative p plus 1, 1 over negative p plus 1 limit t approaching infinity, t to the negative p plus 1 minus 1 to the negative p plus 1. All right, now 1 to a power, all right, this is just going to turn into a 1. 1 to a power is equal to 1. So now we have to focus on that other part. We need to see when is this limit going to converge. And so we're really focusing, we need to focus on this part right here. What's happening there? What's with that limit? All right, so let's consider that. So notice that I can write t to the negative p plus 1 as t to the negative quantity p minus 1. And so then I can think of this as 1 over t to the p minus 1. All right, so now I know that p is not 1. What if p is less than 1? If p is less than 1, then p minus 1 would be less than 0. Now, if p minus 1 is less than 0, so p minus 1 is negative. All right, so let's make sure we understand this now. This says that p minus 1 is negative. Let's keep that in mind. So as t approaches infinity, 1 over t to the p minus 1 would approach 1 over infinity to a negative number. 1 over infinity to a negative number, that would approach infinity to a positive number, which is infinity. Does not converge. Now, what if p is greater than 1? If p is greater than 1, then p minus 1 would be greater than 0. And so understand again, what does this say? If p minus 1 is greater than 0, now p minus 1 is positive. And as t approaches infinity, 1 over t to the p minus 1 would approach 1 over infinity to a positive number, which would approach 1 over infinity, which is 0. And that's a convergence. So what we've just seen is this expression, this whole expression, will only converge for p greater than 1. And so therefore, the integral from 1 to infinity of 1 over x to the p dx converges for p is greater than 1. Now, that was a lot of work, and to do some thinking there, but this is actually a fairly important concept that we're going to use in a later chapter of this course when we deal with what are called, when we're talking about the convergence of infinite series. And we're going to need to use this fact later on, so that's why we have to introduce it now. Now, for the second type of improper integrals, so that is if we have an infinite discontinuity at an endpoint or at a point in between the endpoints, basically what we do is we change to a limit as we approach the endpoint. And if we have the discontinuity within the interval, we break it up into two integrals with limits that approach the endpoint. So, for example, if we have a discontinuity, an infinite discontinuity at b, all right, so if the function is continuous from a to b, and we have that infinite discontinuity at b, so that's this idea, right? So if we had, say, here's a and here's b, and we have some function that's doing this. Right, so we have that infinite discontinuity, and we want to evaluate that integral. What we do is we find the limit as t approaches b from the left. So as we get closer and closer and closer to b on the left of the integral from a to t. And similarly, if we had an integral where we had the infinite discontinuity that's sort of on the left, right, we approach from the right. And if we have a discontinuity at c where a is less than c, which is less than b, we can show that both of the integrals from a to c and c to b are convergent, then we can break up the larger integral as two smaller integrals. So let's consider the integral from 2 to 3 of 1 over the square root of 3 minus x dx. So we first note that there is an infinite discontinuity at x equals 3. And if if you bring up the graph of this on your graphing calculator, you can verify that statement. So since we have the infinite discontinuity at x equals 3, and we're trying to integrate from 2 to 3, what I will do is I will rewrite this integral as the limit as t approaches 3 from the left. I'm going from 2 to 3. I'm approaching 3 from the left of the integral from 2 to t of 1 over the square root of 3 minus x dx. This looks like a good place for a substitution, so I will let u equal 3 minus x, then du is negative dx, and if x equals 2, u equals 1, and if x equals t, u equals 3 minus t. So then I would have the limit with t approaching 3 from the left of the integral. I'm switching from x to u. So from 2, so instead of from 2, from 1 to 3 minus t of u to the negative 1/2 du. Wait a second, I missed something, didn't I? Du is negative dx, so I need a negative in here, so I would need a negative on the outside, and I can bring that outside of the limit. So I have negative limit as t approaches 3 from the left of the integral from 1 to 3 minus t of u to the negative 1/2 du. So this becomes negative limit t approaching 3 from the left. The antiderivative of u to the negative 1/2 is 2u to the 1/2. And we'll evaluate that from 1 to 3 minus t. So this then becomes the negative, let's not forget that, negative limit t approaches 3 from the left. Oh, and I can bring that 2 outside, can't I? Right? That 2 is a constant. I'm allowed to bring that outside the evaluation, and therefore outside the limit. So negative 2 times the limit as t approaches 3 from the left of the square root of 3 minus t minus the square root of 1. All right, so now let's do a little side work here. As t approaches 3 on the left, 3 minus t, well, what happened to 3 minus t? So as t is approaching 3 from the left, so say, for example, 2.999, 3 minus t would be then 3 minus 2.999, that would be 0.0001. So as t approaches 3 from the left, 3 minus t would approach 0. but on the right-hand side of 0, right? Small positive numbers. And so then the square root of 3 minus t would then approach 0. So then we would have negative 2, and let's see, from the limit, the square root of 3 minus t as t approaches 3 from the left would be 0, and the square root of 1 is 1. And so we'd have negative 2 times negative 1, which is 2. And so that integral converges to 2. All right, now for our last example, let's consider the integral from 0 to 5 of w over w minus 2 dw. Now, this looks fairly innocuous, fairly normal, but notice that, that there's an issue here with the domain. Notice that w cannot equal 2 in this function, in this integrand, because we would have an infinite discontinuity. All right, so let's make that note that we have an infinite discontinuity at w equals 2. And so what I'm going to do here is I'm going to think, well, I need to break this up. I'm going to rewrite this integral as the integral from 0 to 2 of w over w minus 2 dw plus the integral from 2 to 5 of w over w minus 2 dw. And so since we have that infinite discontinuity at w equals 2, what I will do is I will rewrite these. The first integral is the limit as t approaches 2 from the left of the integral from 0 to t of w over w minus 2 dw. And the second integral I'll write as the limit as t approaches 2 on the right of the integral from t to 5 of w over w minus 2 dw. Now let me do a little bit of side work here. Notice that w over w minus 2 can be written as, now that numerator is w minus 2 plus 2 over w minus 2, isn't it? And that's sort of a nasty way of looking at it, a nasty math trick. But now I can write this as w minus 2 over w minus 2 plus 2 over w minus 2. Or 1 plus 2 over w minus 2. Now, you would get the same thing if you did a long division on that integrand. So, why would I do that? Well, now the antiderivative of w over w minus 2 dw is then the antiderivative of 1 plus 2 over w minus 2 dw, which is then w plus 2 natural log absolute w minus 2 plus a constant. And so then each of these limits, each of these integrals from earlier, I now have an antiderivative. And so I'd have the limit as t approaches 2 from the left of w plus 2 natural log absolute w minus 2 from 0 to t, plus the limit as t approaches 2 on the right, w plus 2 natural log absolute w minus 2 from t to 5. Substituting, I'd have the limit t approaching 2 on the left. I would have t plus 2 natural log absolute t minus 2. All right, now substituting 0. Minus 0 minus 2 natural log, and the absolute of negative 2 is 2. Plus limit t approaching 2 on the right. Substituting 5. 5 plus 2 natural log 3. Substituting t. Minus t minus 2 natural log absolute t minus 2. Alright, so now let's focus on this part right here. What happens to that natural log of t minus 2 as t approaches 2 from the left? So as t approaches 2 from the left, what happens to first the t minus 2? Alright, so as we're approaching 2 from the left, so that would be, say, like 1.99. 1.99 minus 2 would approach 0, but wait, we want the absolute value. So then the absolute value would approach 0, but on the right-hand side, so small positive numbers. And the natural log of the absolute value of t minus 2, well, now let's think about that. If you think of the graph of the natural log function, remember, as our input approaches 0 on the right for the natural log function, our output goes to negative infinity. So the natural log of t minus 2 would approach then negative infinity as t approaches 2 on the left. So what happens then is, what that tells us is that this part right here, right, this will not converge. That limit, that first limit, does not converge. So then the integral from 0 to 2 of w over w minus 2 dw does not converge. If that one piece doesn't converge, then the entire integral doesn't converge, and therefore the integral from 0 to 5 of w over w minus 2 dw does not converge. So we broke up the integral into its two pieces, and we were able to show that one piece does not converge. So it doesn't matter what happens to the other piece. If one piece doesn't converge, then the entire integral will not converge. All right, that completes the presentation for this section.